Okay, today we're going to talk about the sine of a sum of angles. Now, you've probably seen a proof of this somewhere, but it was not probably a complete proof, because I discovered when doing this proof that you really did need to consider at least two diagrams, and I'll talk about that later. The diagrams are above. So we want to prove the following trigonometric identity: sine of alpha plus beta is sine alpha, cosine beta times sine beta times cosine alpha. We want to look at the entire range of possibilities of angles. It isn't hard to prove in specific cases, but it could be tedious to prove in all cases. But it turns out you need to consider at least two cases. It's useful to learn how to prove a theorem in all cases, because the lesson is about how to be systematic and thorough. And spreadsheets can be helpful. I always have an angle where I bring in spreadsheets. So first, here are some basic trigonometric identities. It'll be useful. Sine of a reflection is minus sine of the angle. Cosine of a reflection is cosine of the angle. Sine of a supplement is the sine of the angle. Cosine of a supplement is minus cosine of the angle. The alpha angles could correspond to any of these 8 regions. Okay, here's some more. Sine of a 180 rotation of an angle is minus the sine of that angle. Cosine of a 180 rotation of an angle is minus cosine of that angle. Sine of a complement is cosine of the angle. Cosine of a complement is sine of the angle. Again, alpha could be in any of the 8 regions. Okay, here is the triangle that we're going to consider. A is the blue side, B is the orange side, C is the green side. Alpha is the angle opposite A, beta is the angle opposite B, gamma is the angle opposite C, the entire angle from A to B. H is the altitude. Now, there's 2 ways to calculate H. H could be A times sine of beta on the left, or it could be B times sine of alpha, which is on the right. Both of them have to give you the same answer, so they have to be the same. It doesn't matter if beta is acute or obtuse. The theorem still applies. That's because sine of beta is the same as sine of pi minus beta. We'll still get the rule that H can be computed 2 different ways. Now it works for right angles as well. In this case, with a right angle, H and A are the same. Sine of beta is 1. Okay, we already looked at that one. This one's pretty similar. And we already looked at a right angle. We could consider that alpha equal to the right angle, 90. So B is equal to A, H. And then in this case, alpha is obtuse, but it's still true that B sine alpha is the height. And we're going to use this triangle in case base case 2. So law of sines is just based on the observation that there are two ways to calculate the altitude of the triangle, so they have to be equal. And that's true for angles that are acute, but it's also true for obtuse angles as well, as we talked about, because sine of pi minus alpha is equal to sine of alpha. So there's several actually different versions of the law of sines. We can write it in any of these possible ways. And we can also compare not just A and B, but A and C. And we get a version of the law of sines that compares A and C or B and C. Okay, this is the base case triangle. This is the one we're going to use to prove the theorem. We need to add the vector v there. That's another altitude. It's similar to h, but this one goes from the intersection of A and C to the line B, or actually the extension of B. Now another thing to note is that C has two pieces, a left piece which is A cosine beta, and a right piece which is B cosine alpha. We'll use that in the theorem. So just take a moment to familiarize yourself with a triangle. We'll use this. So C, as we said, has these two pieces that we're adding together. And then we're going to multiply by sine of alpha. That makes the vector v, the purple vector. And we're going to combine the b and the sine alpha. And the reason why is because we want to use the law of sines. And we substitute b sine alpha with a sine beta. Now we're going to use the law of sines again, but this time with C and A. And now we will be able to compare the term on the left, a sine of pi minus gamma is equal to a times the sine alpha cosine beta times a times sine beta cosine alpha. All right, every term is divided has a is not 0, so we divide through. And now we use the fact that the sum of the angles in a triangle are pi, so we can write that as sine of alpha plus beta. And that's exactly what we wanted to prove, by the way. Well, case 2, we're going to consider this triangle, and we're actually going to use alpha prime, not alpha. Alpha prime is the external angle, and one thing to note about external angles is they sum up to, alpha prime sums to beta plus gamma. Another thing to note is that C is now the difference between two things. It's a cosine beta, that's the whole length to h along the axis, and then minus the dotted line, which is b cosine alpha prime. So it's a difference, not a sum this time. Another difference is that v is now below the baseline, but it doesn't really change anything about how you would calculate v. Okay, so alpha prime and beta. We're going to use the fact that C is equal to a cosine beta minus b cosine alpha prime. We're going to multiply that by sine of alpha prime, just the way we did in the first version. And then we're going to combine the b and the sine of alpha prime, because we want to use the law of sines. And we're going to change b sine alpha prime with a sine beta. And then we're going to use the law of sines again with c and a. And we're going to compare a sine of gamma with the term above. And once again, we're going to divide by a because a is not 0. And we get something that looks familiar. Gamma, keep in mind, it's equal to alpha prime minus beta. Looks like the rule, but with minus signs instead of a plus sign. But we can change this to something that looks more like the original version by treating minus beta as the angle. And if we treat minus beta as the angle, then we get the sine alpha cosine beta plus sine beta cosine alpha form on the right hand side. Now that we've proven both base cases, we need to think about other cases. Alpha could be in any of these 8 regions. Beta could be in those 8 regions. That's 64 regions. And then the sum, alpha plus beta, could be in multiple regions. Turns out there are 96 cases to consider. And many of these do not have a triangle that you could use. So what to do? Well, we'll talk about that. Our general strategy will be we'll extend the base cases to an entire quadrant times quadrant. So base case 1 is first quadrant times the first quadrant. We'll extend that. And then base case 2 will extend to quadrant 1 by quadrant 4. And then we'll have some theorems that allow us to very quickly extend these 2 base cases to the other 14 cases. The other 14 cases are Q1 by Q2, Q1 by Q3, Q4, all the way up to Q4 by Q4. So the commutation operation, commuting means sine of alpha plus beta should equal the same thing as sine of beta plus alpha. That's easy to prove. I mean, just rearrange the terms on the right hand side into the opposite commuted way, and that's literally sine of beta plus alpha. So commutation is a theorem that we can use. Okay, adding 0 lemma. We can directly add 0 to beta, take the sine, and we'll get sine of beta. But would we get the same result if we plugged in 0 in the sine alpha, cosine beta, etc. formula? So sine of 0 is 0, cosine of 0 is 1. When we plug it in, we get sine of beta, which is exactly what we would expect. So in other words, adding 0 is as you would expect. consistent with the formula. Sum of supplemental angles. Okay, suppose you have two angles that sum to pi. Well, obviously you're not going to have a triangle there. Sine of pi is 0. Would you get the same result if you plugged into the cosine alpha, cosine beta, etc. formula? Well, let's plug it in and see what happens. We get because sine of a supplement is the same as the angle, but cosine of the supplement is minus, the two pieces cancel, and we're going to get 0, which is consistent. We're good to go. So let's look at the 11 subcases of Q1 by Q1. So we're looking at different possibilities for alpha and different possibilities for beta, and the sum alpha plus beta. So 0, 0, 0. There's 3 cases where alpha could be 0, beta could be acute, and therefore alpha plus beta would be acute. Beta could be 90, and alpha plus beta would be 90. Then there's 5 cases where alpha is acute. Beta could be 0, and therefore the sum is acute. Beta could be acute, and the sum could either be acute, it could be 90, it could be obtuse. Then beta could be 90, and the sum would be obtuse. Then there are 3 cases to consider where alpha is equal to 90. Beta could be 0, and so the sum is 90. Beta could be acute, and the sum would be obtuse. And beta could be 90, and the sum would be 180. Now, some of these cases are really easy to prove, like the first one. That's obviously adding 0 lemma. In fact, the first 3 are the adding 0 lemma. And 4, that's also a version of the adding 0 lemma, but that's a commutation of the second case. And 9 is a commutation of the third case of the adding 0 lemma. Okay, and the one more easy one, 11, the angle sum to pi, we have a rule for that, supplemental angles lemma. Okay, now let's look at the base case. That's 5. Well, we proved the base case, so we're good to go. But what about 6 and 7? What role does gamma play in this proof? If gamma were 90, would that make a difference? If it were acute, would that make a difference? Actually, no, it doesn't enter into the proof at all. So it's essentially the same proof. Well, let's look at 8. What if beta were a right angle? How would that change things? You could see what the difference would be pretty easily. That one of the two pieces of C would actually be 0. There would only be one piece of C, the one that's right of H. But that doesn't make anything else about the theorem wrong. So it's a natural extension of the base case. And 10, it's just a complement of 8. A commutation of 8. Okay. Reflection operation. If I do not know that sine of alpha plus beta, the theorem applies, but suppose I can pull out a negative sign, and then the theorem would apply. I could use my sine alpha, cosine beta rule on those negative reflected angles, and then I can use the fact that cosine of a negative angle is just the same as the cosine of the angle. And then I use the fact that sine of a negative angle is minus the sine of that angle. And the minus signs cancel. And I just get the sine alpha, cosine beta, etc. Okay, difference of equal angles lemma. Suppose I calculate the sine of a direct calculation of sine of alpha minus alpha is sine of 0, which is 0. But if I plug it into the sine alpha cosine beta formula, what do I get? Well, it's easy to see that the cosine of a minus is the same as the cosine of the angle, but the sine is negative, so I have equal and opposite terms that cancel, and I get 0. All right, let's look at the 11 subcases of Q1 by Q4. Diagrams off to the right for your to refresh your memory. And we're going to go through different cases of alpha and beta. Now notice that we're doing minus beta, so the minus beta, all the angles will be either 0 or negative. So alpha prime could be 0, beta could be 0, acute, negative 90. Alpha prime, there's 5 cases where it could be an acute angle, beta could be 0, beta could be a negative acute angle, and then the sum could be either a positive acute, it could be 0, or it could be negative acute. And then if beta were negative pi over 2, then the sum would be negative acute. If alpha prime is pi over 2 and minus beta is 0, then we have pi over 2. If it were negative acute, we get acute. If we get minus pi over 2, then we get 0. Okay, so let's go through these cases and think about, well, what rules can we use? Well, one we've already done. That's the adding 0 lemma. In fact, the first 3 are the adding 0 lemma. And then 4, that's also the adding, that's a commutation of the adding 0 lemma. 9 is a commutation of the adding 0 lemma. Okay, 11, that's an easy one. That's the 0 sum lemma. 6 is also the 0 sum lemma. Okay, that's the easy ones. Now, we need to consider the base case. We proved that one. But what about 7? 7 is a positive angle minus a negative angle, giving me a negative angle. That's where we use the reflection. Reflection turns all the negatives to positive and the positives to negative. But I also need to use a commutation. And I can use the combination to compare it to case 5. Okay, let's look at 10. This one's sensible. Here, alpha prime is simply a right angle. That could be. It doesn't actually change the theorem much. The dotted line there, it doesn't exist. C is just everything. So this is the base case 2 extension. And then for 8, that is a commutation reflection. Okay, a rotation operation. Adding 2 pi to an angle doesn't actually affect the sine or cosine. So we'll split that 2 pi to each of the angles, and then we'll apply our rule, and we'll discover that since sine of a rotation or cosine of a rotation is just the negative of the angle, and all those negative signs cancel, we'll wind up exactly with what we would want. Supplemental operation, we're going to use the rule that sine of alpha plus beta is the same as sine of pi minus alpha plus beta quantity. We'll split that up into 2 pieces. We'll apply our rule, and then when we go through all the math, once again, everything nicely combines to give us exactly the rule that we wanted. Okay, we'll apply the 4 major operations to the 2 base cases: commutation, reflection, rotation, and supplementation. Each operation we perform twice puts us back to the original situation, so each operation is its own inverse. One implication is that if we can go from A to B, we can go back from B to A as well. If you add the 2 quadrant numbers together, you get either an even or an odd number. It turns out the 4 major operations map evens to evens and odds to odds. This is why we need 2 base cases, an even one and an odd one. Okay, let's look at the 14 additional cases, Q1 by Q2, etc. Okay, this will go quickly. So we have the case 1, and I put the 4 quadrants off to the side so you can kind of see what it is. 1, 1, those are acute, positive, and we're going to go to acute, negative. That looks like a reflection across the x-axis. Okay. 1, 1, 2, 3, 3. I can see that as a 180 rotation. 3, 3 to 2, 2. Oh, that's a reflection over the x-axis as well. 1, 1 to 2, 4. That is a supplementation. 2, 4 to 4, 2. That's a commutation. Might also have been a rotation. There might be more than one answer, correct answer. 4, 4 to 3, 1. That's a supplementation. 3, 1 to 1, 3. That's commutation. Okay, that's the even cases. Now let's consider the odd cases. 1, 4 to 4, 1. Okay, don't have to overthink this. This is just a commutation. One 4 to 2 1. That's a supplementation. 2 1 to 1 2. Again, that's a commutation. 1 4 to 3 2. That's a rotation. Three two to 2-3, commutation. 1-2 to 3-4. That's a rotation. Three four to 4-3, commutation. Okay, one last thing. The cosine rule. Cosine of alpha plus beta, I can write it as its complement using the sine formula. I can break it up into two angles and apply my sine rule. And when I look at each piece, I look at the sine of the complement, that's a cosine. Cosine of a complement, that's a sine. Cosine of a negative angle is just the angle. Sine of a negative angle, I pull the negative sign out. That's the rule. That's all you had to do to prove it. Okay, time to close the spreadsheet. Thank you.